Alright guys, welcome back. We got a pretty short lecture today on section 2.3. This is again one of those sections I mentioned where it's predominantly terminology. I'm actually going to go over this one just because I want to try to connect this to some of the things that you've done in your previous mathematics courses, right? I actually trust that you can read through the chapter and learn all the terminology yourself. As such, there's no actual prerequisites for this because the point of this section is just so that you and I will have the same vocabulary when we're speaking about these things. So we have terminology for linear systems. So the first question I would probably ask is, what's a linear system? And we refer to a system as a group of equations which all use the same collection of unknowns. And linear has an interesting definition. We teach students in very, very young grades, like 8th grade, things like that, that linear sounds like line, it means line. And in reality, that's true. Lines are linear, the equations of lines are linear, but other equations are linear as well, right? So for example, let's say 3x plus 2y minus z equals 4. This is not a line, okay? This is not a line. This is a plane, actually. This is a plane that exists in 3 dimensions. But this equation is linear in x, it's linear in y, it's linear in z. Now later on this semester, we're going to give a more formal definition for what linear means. For right now, sort of a useful idea is that something is linear if you can solve for the variable by using addition, subtraction, and dividing by constants, right? And again, that's not exact, but that's a useful sort of mental shortcut right now until we get to the actual definition. So again, I can solve for x, y, and z by adding and subtracting terms to either side of my equation and dividing by constants, okay? So referring to a linear system means that I'll have several of these. Now, one of the things we're gonna do here is we're gonna change up our notation here. This is a perfectly good example with 3 variables, but could I have had 4, or 5, or 6, or 7, or 8? Yeah, okay. And since we don't necessarily know how many variables we're gonna have, we're gonna index our variables, okay? So as a convention for this course, okay, whenever we write things like this, we'll just call the first variable x1, the second one x2, the third one x3, so on and so forth. That way we don't have to worry about having to come up with lots of different letters in case we have a whole bunch of variables. Okay? All right, fair enough. Okay? So a linear system then would be several of these equations. Now I'm going to write it in a general form, in a general index form, because I want to be able to describe some aspects of this. Okay? So I'll write my first sort of general linear equation here as a1 x1, a1 is my coefficient, x1 is my variable, plus a2 x2. I don't actually know how many of these are, so I'll just say there's n, so we go out to a sub n, x sub n. Okay? And this is equal to some constant b sub b1, b sub n, b1. It's the first one. Okay? Fair enough. Okay? Now I want to be able to write a second equation, but the problem is, do I want to use another letter? Well, I know my variable would be the same, but I need a constant here. Well, what if I want to use a again? Well, the problem is I can't use a1. So what if I index this as a11, equation 1, first variable, and call this one 1, 2, equation 1, second variable, and this one a1n, equation 1, nth variable. Okay? Then in that case, this constant would be second equation, first constant. So I keep saying variable, first constant. This would be second equation, second constant, etc. This would be second equation, nth constant. And hopefully by now you're starting to see how the matrix notation is going to end up coming in here, right? Now, how many of these do I have? I don't know. Some. Okay. I don't have to have n of these, right? I could have fewer. I don't actually know. Let's say I have k of them. Well, let me use the same letters your book uses. What does your book use? M. Yeah, that makes sense. Okay. I'll use M. So M1. All right. Here we have A sub M2. And I have Mn. B sub M. Okay. And now I've got a whole bunch of these. Okay. We're familiar with notation, right? These are coefficients. These are variables. These are called the constants of my linear equations because they have no variable attached to them. Okay. And if, okay, so if b sub I equals 0 for every I, so that is if every one of these constants is 0, then the system itself is said to be homogeneous. Okay, it's said to be homogeneous, right? So homogeneous just means that all the constants here, all the constants there are 0. Okay, and what if they're not all 0? Well, then it's non-homogeneous, right? It's the exact opposite of non-homogeneous. Makes sense. Okay. Fair enough. Okay. I would call solutions to this a solution set, right? So any solution would be a collection of values that I can plug in for x1, x2, all the way up to xn, and it will satisfy all of these equations, okay? All these things work just fine, okay? Now, you've solved some equations like this before in lower level classes, in lower level algebra, right? Let me give you a quick example. Okay, so you've solved things like, for example, let's say 2x minus 3y equals 7 and x plus 2y equals -1, right? And you were told to solve the system. This is the same thing, it's just a much smaller version. This is a 2 by 2, right? Okay, let me adjust our notation, okay, just to be consistent. x1, x1, okay, I just don't want to start doing, okay, and x2, x2. And I know this sort of takes away the geometric thought here because you were taught that those were lines on a plane, but we're going to be dealing with higher dimensional objects. So, and you were given a couple different versions on how to solve this, right? You were told that you could do it by substitution. What does substitution mean? Substitution means that we solve for one variable. So let's say I solve for x1, and I would have x1 equals -1 minus 2x2, then plug that into my other equation. That would work. The problem with that method is, while it would work, doing that for a system of like 6 equations with 6 variables would be a huge pain in the butt. Ultimately, we learn the elimination technique, which is to say, let's say I multiply one or both of my equations by a number, and then get it to where the corresponding coefficients are now additive inverses, right? So for example, if I multiply my bottom equation by -2, this would be -2x1 minus 4x2 equals +2. Then I can add the two equations together. That'll remove one of my variables. But again, doing that for a very large system is a lot of steps. So what are we going to do? We're going to do something else, okay? The first thing we're going to do is I want to be able to represent this in a form that is not several equations written all together, right? And so we're going to write this in a matrix form. I would like to write this as a product of a matrix times a set of variables, and then equal to, again, maybe some other constants. Okay, so let me go ahead and define a matrix here. So I've got 2, -3, 1, 2. And of course, where did I get these numbers? Well, I just took the coefficients from my variables, right? And now I'm going to define here my unknown vector, or my variable vector, and I'm going to make this one x1 and x2. Okay? All right, and now I've got my constant vector. And now I claim that this and this represent the same form, right? Remember how we multiply matrices together. You take row times column. So if I take the first row times the first column, that's row 1, column 1, that's 2 times x1, -3 times x2, and that should be equal to the 1, 1 entry, 7. That's exactly what this is. So row 1 times column 1 equals the 1, 1 entry. That's my first equation. Row 2 times column 1 gives me my 2, 1 entry. This is the same. And if I wanted to label this matrix A, that matrix, well, vector matrix X, variable vector X, and this one B, I get A times X equals B. That's a very, very simple way of writing these equations. Now, why? Why do I want to write these? Well, it turns out that we can solve these systems without actually having to work with the variables themselves, right? What we can do is we can write what are called the representative matrix, or the coefficient matrix, and the augmented representative matrix, or the augmented coefficient matrix, and we can work with those. Okay, so again, let me, where's my eraser? Here it is. Okay. Okay. So I'm going to define a few things here. So, oh, I shouldn't have erased that. Crap. Hold on, let me write that back up here. Okay, and X1. See, I erased it, but I'm able to copy down the exact system again just from these things. It's pretty nice, right? Okay, so, and these are going to be the most important things for us over the next few sections. Okay, so I'll define two things. One, I'm going to define a matrix A. This is just my coefficients. Okay, and I'm going to call this, okay, I'm going to call this my representative matrix A. Okay. This is, again, these are also called coefficient matrices sometimes. I can't remember right now which one your book uses. It doesn't really matter. Okay. Now you'll note that this is not enough information to handle my system, right? Because you would think, and it's perfectly logical, that the solutions would change based on these numbers, and I don't have these numbers anywhere in here, right? So this is not actually enough. So I want another one. I'm going to call this one A pound, right? Minus points if you call it A hashtag. I hate you so much. Okay? All right. And this one is exactly the same as A, except it's got an extra column. Okay? And this extra column is just going to be those coefficients, the constants from my system, right? So I'll just tack on the column 7, -1 on the end. Okay. This one we're going to call our augmented representative matrix A. And this, to be perfectly honest, this is the one Well, this is the matrix we're going to use for basically all of these things. From this matrix, in the next section, we are going to learn some operations to whereby we can use this, and exclusively this, to solve our system. Okay? Now, this is the reason a lot of you that are in computer science are taking this course, right? Okay? The ability to represent this information as an array, as something efficient and something clean, okay? This is why those people are taking this course, okay? So it's easy when we start getting into working these problems to forget what they mean, right? Because once you have a giant grid of numbers and you're just kind of dialed into mashing the numbers around, and it takes you 30 minutes to get done with doing those things, sometimes we lose track of, well, yeah, but what do those numbers actually mean? These things represent an equation. These represent lines, right? This is literally a line, that's another line, and this is asking me where or how do those lines actually intersect, okay? So I will be stressing the geometry, okay, as we go through some of these things, and I want you guys, when you do the homeworks, to try and do that too, to try and imagine the geometry for these things, okay? All right, like I said, this is a very short lecture. I just wanted to introduce those things. I'll put 2.4 up at some point in time. You guys have homework to do, so again, I'll see you next time.